Okay, here's a typical sample problem from Newton's second law. You are given two objects, M1 and M2, that are connected by a string over a frictionless, massless pulley, and an inclined surface is also given to be frictionless. And the values of the masses are given and the angle of the ramp is given. And you're asked to draw the free body diagram for both the objects and also calculate the acceleration and the tension in the string. Right. Now, since these two masses are connected to each other, the two situations are either M2 is pulling M1 down, M2 is coming down the incline, M1 is going up, or the other way around. If M1 is heavy enough, that would be pulling it down and M2 would be going up. Now, when we look at the values, M1 is 2 kilogram, M2 is 4.55 kilograms. It looks like M2 is the one that will pull it up. If you really want to know, you could calculate M2g sine theta and see if it's bigger than M1g, but it's not necessary. You could just assume, suppose the component of the weight of M2g is larger than the weight of M1, then the acceleration would be down the incline for M2, and because of that M1 will go up, right? That will accelerate upward. Same acceleration for both the objects. And in case I assumed it wrong, my math will tell me in the end, if I get a negative value for acceleration, I can go back and say I assumed it wrong, you see. So anyway, so I have the direction of the acceleration given there. Now I have to draw free body diagrams for both the objects, right? So if for M1, for example, we have for M1, if I show M1 by this, I have its weight downward and the tension in the string, which happens to be same on both sides of the pulley, right? Because it's a massless pulley, right? And so the tension's got to be bigger than its weight, so that there is an unbalanced or net force in the upward direction. That's why it's accelerating upward, right? And similarly, I can write for M2, the free body diagram is, I've got my M2 here, right? See, that's M2, and it's got its weight. So M2g is downward and it's heavier, so I'm making it longer, M2g, and the surface of the incline is pushing up on it, so there is a normal force that way, and there is no friction. It's a frictionless incline, but there is a tension in the string which is pulling on it, right? So that's the tension T, you see. And as a result of these three forces, it's accelerating downward. Okay. So now the question is, find the acceleration and the tension in the string. So if we look at the problem, we have two unknowns in the problem, right? So we have two unknowns, and the two unknowns are the tension and the acceleration, T and A. So that means we need two equations, right? So that we can solve them for the tension and the acceleration, right? So the next thing to do is to convert these free body diagrams into equations. So if I'm looking at M1, I'll say for M1, let's see, I'll say for M1. For M1, if I use Newton's second law, net force is mass times acceleration, and since the motion is completely in the vertical direction, I'll say in the y direction. And net force in the y, remember the direction of the acceleration is the positive direction in this chapter, so we'll write this as T minus m1 times g is equal to m1 times a, right? And that gives me my first equation. Okay, same way for M2, I can say I have one equation, net force in the x is mass times acceleration. And by the way, as you know, for inclined planes, we take the x-axis to be along the incline. So this is our x-axis here, and y-axis is perpendicular, right? Y-axis is perpendicular to the incline, and the angle of the ramp is theta. So if I drew this here, right, that's our y-axis, this is our x-axis here, and if the angle is that, if I draw my m2g here, if this is theta in this right triangle here, this would be 90 minus theta, so this would be theta, right? So in my picture here, this is the angle theta of the ramp that it makes with the y-axis, right? This is the y-axis. Okay, so I can take the components of m2g, both parallel and perpendicular to the incline. So when I drop this perpendicular onto the x-axis or down the incline, that's my m2g sine theta, and that's sine because it's opposite to the angle theta. And then the one that's perpendicular to the incline is m2g cosine theta. Okay, so now I can write my equations. Net force in the x is mass times acceleration. So when I look at the forces down the incline, acceleration is down the incline, so that's my positive direction. So m2g sine theta has to be bigger than the tension that's going against it to give it an acceleration a. You see, so that gives me my second equation, right? So that's my second equation. I also have a third equation, but I don't really need it for this problem, but we can just for completeness, we'll write it out. Net force in the y is mass times acceleration, but there is no acceleration in the y direction perpendicular to the incline, so this is 0, and the net force is n minus m2g cosine theta equals 0, or the normal force is equal to m2g cosine theta. I could call it a third equation. I don't need it here. It will become important when we introduce friction into the problem, right? But right now, we don't really need it. I'll leave it alone. We'll mainly look at equations 1 and 2 to solve for the two unknowns. So you can solve it however you like. You could substitute for t from one equation into the other and solve for the acceleration. Or whenever I see a t and a negative t, I'm tempted to just add the equations, so that way the t gets cancelled, right? So if I do equations 1 plus 2, that will give me, I'm adding the left-hand sides together, so I have t minus m1g, and then I add the left-hand side of equation 2, so that's m2g sine theta minus the tension, that's equal to the sum of the right hand side, so that's m1a plus m2a, right? So I can get rid of the tension and the minus tension. So what I've got is m2g sine theta, this is the component of the weight down the incline, minus the component that's inhibiting the motion, that's the weight of m1, and that's equal to the sum of the masses m1 plus m2 times the acceleration. You see? And I just want to show you that we could have gotten to this equation just by looking at the system. If you see here, m2g is the force, the weight downwards. So the force that's pulling on this down the incline is m2g sine theta against the smaller m1g that's pulling, trying to resist from the acceleration. So the total force on the whole system is m2g sine theta minus m1g, because tension becomes an internal force then, and that net force is accelerating a total mass of m1 plus m2 with an acceleration a. Right? So that's what this equation is telling you, and you can go from here and you can solve for the acceleration. right? So the acceleration will be m2g sine theta minus m1g divided by sum of the masses. And our m1 and m2, m2 was, I believe, 4.55 and m1 was 2 kilograms. So this was 4.55 kilograms, 9.8 times sine 53 minus m1 was 2 kilograms and g is 9.8 meters per second squared divided by 4.55 plus 2. And if we calculate it, this comes out to be 2.44, three significant figures, 2.44 meters per second squared, right? So that's the acceleration of the system. A1 as well as A2 both are equal to that acceleration. Okay, and of course once you have that, it's easy to get the tension. You could either substitute into equation 1 or equation 2. Either of them should give you the tension, right? So if I go ahead and substitute into my equation 1, my tension T is going to be m1g plus m1a. So that's 2 kilograms times 9.8 meters per second squared plus 2 kilograms times 2.44 meters per second squared. And if I substitute that, I see that it's 24.5 newtons. Okay. Now you could have also used equation 2. I would strongly recommend using equation 2, and you should be able to show that it gives you the same tension, 24.5 newtons. Okay, so very typical of these kinds of problems. This is how you do them. And there is another part to this problem which says find the speed of each object 2.75 seconds after being released from rest, right? So assume the inclined plane is really long, so it hasn't quite reached the ground yet, and it's also really tall, so m1 hasn't quite gone up all the way. So this is where if I'm looking at m1, for example, I just concentrate on m1, that has got an acceleration in the upward direction, and we know that acceleration 2.44 meters per second squared. And the question is, if it's released from rest, meaning if the initial velocity is 0, find the speed, meaning at the end of the second, so they're asking for the final velocity, right? So since time is given, t is 2.75 seconds, you could just use your first kinematic equation, Vf equals Vi plus At, and Vi is 0, acceleration is 2.44 meters per second squared multiplied by the time, 2.75 seconds, and if you calculate it, you'll get it comes out to be, sorry, that was a mistake. If it's 2.44 times 2.75, that will be 6.71 meters per second. We could have done it either for this or for the mass m2. We would get the same result, right?